In this video, we're going to look at another way we can write functions that take decisions in Haskell. So previously, we've written this tree member function by using an if then else or guards. So let's just write that out again. So we're looking for a member x in leaf, that's going to be false. We're looking for a member x in a node with a left subtree, a value in a right subtree. And we might write this using guards as if x is equal to y, then we return true. If x is less than y, then we search the left subtree for x, and otherwise we search the right subtree. Now this is all very well, but if then else and guards have a common problem, which is that we can only use them to test things which are either true or false. And there's no connection, in some sense, between the different lines here. It checks this one to see if it's true. If it isn't, it falls true. And if it isn't, we just have this catch-all case at the end. And we have to think for ourselves that the catch-all case really is doing all the greater than parts by thinking, well, if it's not equal and it's not less than, then it must be greater than. Another way of doing this in Haskell is to use case expressions instead. And case expressions allow us to pattern match on data types rather than just testing things for true and false. So let's see how this works. So what I'm going to do is just rewrite this straight away using a case expression and then explain it. So what we're going to do is case compare x, y of, and either they're equal, so we return true, x is less than y, so we do tree member to x in the left subtree, or it's greater than, we do tree member to y, x in the right subtree. We're going to delete these parts. This does the same job as before, but rather than this list of Boolean conditions, we now have a comparison where it returns one of three answers, either equal, less than, or greater than, and then we use a case expression to decide what to do. And we can explore this code ourselves in the REPL. So we can look at the function used, that's compare, and we can ask using info what is the type of compare. So we can do this and say, well, compare takes two a's, which are ordered values, they're type as a member of the ordered type class, and return something of type ordering. And then we can ask, well, what's an ordering? An ordering is something which is a data type which is either less than, LT equal, EQ, or greater than, GT. And then it's an instance of all these different type classes, which we'll come back to later in the course. So now we can just try less than is less than, what's the type of less than, it's an ordering. And if we try compare, we can try comparing 1 and 2. As you might expect, it says that 1 is less than 2. We can try comparing 1 and 1 is equal, and can try comparing 2 and 1, and 2 is greater than 1. So now this tree member 2 is just a different way of writing tree member, though instead of using guards, we can use the fact that compare returns an element of a data type, and then we can write all the patterns down here, just as we do on the left-hand side of an equals, so here, on a function definition. And in general, case expressions look like this. We have case, some expression in here, of, and then pattern 1, and code 1, and then we just have a list going down, all the way down to pattern n, code n. So when I say code here, this is just the code that tells Haskell what to do in that case. And as with patterns in functions, it will warn us if we don't have enough patterns, and it will also make sure that the patterns are not redundant. So if we try and write the same thing twice to try and be inconsistent, and then we reload that, then it will say pattern match is redundant, and it does the same thing for functions as well. So if we try and be ambiguous, it won't let us. So let's see what we can do with this. Let's have a slightly bigger example than the ones we've seen before of a function. So this function, what it's going to do is make change. So before the pandemic, people used to pay for things using coins, and now we all use contactless, but In a while ago, it was a reasonable thing to do to say, well, I've got this list of coins, 50p, 20p, 20p, 10p, 2p, 2p, 1p, 1p. And let's say we want to make 54p, then there are 4 ways of doing it. So we can either use 2 2p's and 50p, 2 1p's, a 2p and 50p, and so on. So we're going to write a function that's going to search for one way of doing this. It's going to try and find a way of doing this. We give it a list of coins to use, an amount, and it's going to try and return a way of making change from those coins. So here's our setup. So first I'm going to make a type synonym. So rather than using int for coins, or explicitly saying int for coin, I'm going to make a type synonym and say type coin equals int. So this allows us to write test coins, which is a list of coins. And then here's my list of coins that I had before. And now the main function is going to be this make change function. And this is going to take a list of coins which are available, a list of coins which we've used so far, the amounts we're still trying to split up into coins, and then it tries to return a list of coins that are the ones which we can split up this amount into. And this is going to be a maybe, because it may not be always possible to split up all the split up the amount into the coins we have. So let's see how to write this function. So let's say we've got a list of available coins, we've used some coins, but the amount we're splitting is 0. So in this case, we're done. We can just say return just the used ones. There might be another case where we've run out of coins, we've used some, but the amount we're trying to split into is some n. And now because this line matched any amount of available coins and any amount of used coins and 0, this n must be non-zero. So in this case, we can say nothing. There's no way of splitting up a non-zero amount of money using 0 available coins. Now the more interesting case is where we have one coin at the top of the pile to be used, those available, and we have some amount of money that we want to split. Now, there's 2 options here. One is that the coin is too big, so we can't use it to split the amount of money. So we have to check that the coin is less than or equal to the amount we're splitting. So we'll just do that with a guard. And then we simulate the using of a coin by saying we're going to continue making change with the remaining coins. We add this coin to the used pile, and we subtract the value of the coin from the amount we're trying to split. Otherwise, we skip over this coin, so we carry on with the rest of the coins, we don't update the used pile, and we don't update the amount we're trying to split. So let's give this a go. So let's load it in, and then we can do make change with our test coins, and let's try and, well, we have to start with the empty list of used coins, and we start with 54 pence. And indeed it tells us that one of the options is to split it into 2 2p's and 50p. So does this work? It seems like it worked on this small example. Let's try another one with a slightly odd set of coins. So let's say we've got a 50p, 2 20p's, 11p, a 2p and a 1p. Now we try and split 54 using these coins, and it says nothing. However, we could have split it. We could have split it into 20 plus 20 plus 11 plus 2 plus 1, and we would have got 54. So what went wrong? So the problem was that our search was greedy. As soon as we found a coin in the pile, which was smaller than the amount we're trying to split, we said, aha, let's use this coin, and then carry on. So what actually happened was the following steps. We tried to do make change with this set of coins. So there's 50, 20, 20, 11, and 2 and 1. We had the empty set of used coins, and we had 54. And then what it did was, it checked 50 against 54, said, okay, 50 is less than 54, so we're going to call make change again with 20, 20, 11, 2, 11, 2 and 1, and we'll put 50 on the used pile, and then we've got 4p left. And then we're going to step through, so 20, 20, 11 are all not less than 4, so we skip over those, so there's a few dots. And so we get down to 2 and 1, so we're still using 50p, and then 2 is less than 4, so we can use that. So we've got 1 left. We add 2 to the list, and we've got 2 remaining to split. But now we can see we're in trouble. So we've got 1p remaining, but we need to make 2p. So we're going to use the 1p because it's less than 2. Got 1p remaining, and now we're in the case where we've got no coins left, but the amount to split isn't 0, so we just end up returning nothing. So how do we fix this? So one way is to use backtracking. So what we're going to do is to say we're going to try this line here, we're going to try using this coin, so in this case the 50p, and then we subtract it. But if this doesn't work, then we're going to undo that change and go back and try again without using that coin. So we can do this using a case expression. We're going to say case this thing of, and now this thing returns a maybe. So if it failed, that is it returns nothing, we change our mind. We don't use the coin. So we're going to call make change again with coins, the same used as before and the same amount as before. But if it did work, then we just return the successful solution. So let's see if this works. So this is our set of odd coins. We're going to split 54 again, and indeed it does work. We get the expected solution 1, 2, 11, 20, and 20. We'll just test again with our test coins. There we get the 2, 2, and 50p from before. So this shows you how to make a relatively complex function and using a case expression in order to use the recursive result of the function and make a decision based on that. So we're no longer just limited to writing just functions applied to things on the right hand side of an equals. We can apply functions to things and then take more decisions based on the return values of those using a case expression.